Differentials like linear approximation can also be used to approximate roots. Even with similar tangent line concept, a little variation in the procedure will be observed. Welcome to differential calculus. From the previous video, differentials were introduced with the equation of dy as equal to f prime of x multiplied by dx. Ideally, dy should be the same as delta y. From the given formula, dx, dy, and delta y should be determined first. Let's find the root of 90 using differentials. The equation we would use is dy equal to f prime of x times dx. So we needed to determine dy, f prime x, and dx. F prime of x is the derivative of the function, where the function for this case is the root of x, which we can write as x raised to 1/2. F prime x is the derivative of x raised to 1/2, and that is half of x raised to negative 1/2. To do away with the negative exponent, we rewrite the expression as 1 over twice of the root of x. This is f prime x. So dy can be written as 1 over 2 times the root of x times dx. The next things to look for are dx and delta y. The number in the premise is denoted as x sub 1. For this example, we have 90 as x sub 1. Then we look for another point with x which is close to 90. Say we get 100. Why 100? It is because this is the closest perfect square from the premise. Knowing the two x's, we can determine delta x from their difference. That is the absolute value of 90 less 100, which is 10. Take note that delta x is the same as dx. The last parameter to look for is delta y, which is the difference of the functions of the two x's. So we get the root of 100 minus the root of 90, simplified as 10 minus the root of 90. Having known all the parameters, we can equate delta y to dy. We get 10 minus the root of 90 is equal to 1 over 2 times the root of x times dx. Plug x and dx into the equation to have 10 minus the root of 90 is equal to 1 over 2 times the root of 100 times 10. Then transpose 10 to the other side to isolate the root of 90. Simplify the whole expression to come up with negative root of 90 equal to negative 9.5. Finally, the approximate root of 90 is 9.5. Compare this with the exact root of 90 as 9.4868, which is close to 9.5. The next example is to use differentials in approximating the cube root of 112. Knowing the formula for dy, we clear out f of x, which is taken as the cube root of x, written as x raised to 1/3. For f prime of x, take the derivative of x raised to 1/3. This is 1/3 of x raised to negative 2/3, which can be written as 1 upon 3 times the cube root of x squared. This is f prime of x, which is plugged into the equation of dy. Next is to identify 2 points with their x coordinates, one from the premise, x sub 1 as 112, the other x is based as the closest perfect cube from x sub 1. With the x's known, We can find delta x as the difference of 112 and 125, which is 13. This is also dx. The next is delta y solved as the difference between the functions of the x's. That is the cube root of 125 minus the cube root of 112, simplified as 5 minus the cube root of 112. Now we are ready to equate delta y with dy. We have 5 minus the cube root of 112, and this is equal to dy, which is 1 all over 3 times the cube root of x squared. Then multiply this by dx. Place the solved values of x and dx to have 5 minus the cube root of 112 as equal to 1 all over 3 times the cube root of 125 squared times 13. Reduce the term to make the equation 5 minus the cube root of 112 as equal to 1 over 3 times 25 multiplied by 13. Then transpose 5 to isolate the cube root of 112 and simplify the terms to have negative cubed root of 112 as equal to negative 5 plus 13 over 75. So the approximate cube root of 112 is 362 over 75, or 4.8267. This is close to the exact cube root of 112, which is 4.8203. What if we were to deviate a little further from x sub 1? Say we take the cube of 4, which is 64. Let's continue with delta x as 112 minus 64 to have 48, and this is the new dx. Delta y is also computed as the cube root of 112 less the cube root of 64, simplified as the cube root of 112 minus 4. The next step is to equate delta y with dy. We start with the cube root of 112 less 4 and equate this to 1 over 3 times the cube root of x squared times dx. Place x and dx into the equation. These are 64 for x and 48 for dx. Then transpose 4 to the other side. Finally, the cube root of 112 as 4 plus 48 over 48, which would give the approximate cube root of 112 as 5. This has a bigger discrepancy from the exact cube root of 4.8203. Let's try to determine the fifth root of 34 cubed using differentials. The function for this case is the fifth root of x cubed, written as x raised to 3/5. Its derivative is 3/5 of x raised to negative 2/5, also written as 3 over 5 times the fifth root of x squared. So dy is completed as 3 over 5 times the fifth root of x squared times dx. X sub 1 is from the premise, and that is 34, while x is the closest fifth power from x sub 1, and that is 32. Now delta x is the difference of the two x's, giving 2. This is also dx. Delta y is then computed as the fifth root of 34 cubed less the fifth root of 32 cubed, and simplified as the fifth root of 34 cubed minus 8. Having these two parameters determined, move to the equation delta y as equal to dy. Delta y being the fifth root of 34 squared minus 8, and dy is 3 over 5 times the fifth root of x squared times dx. Place x as 32 and dx as 2, both of which are computed earlier. Then transpose 8 to the other side, making the equation the fifth root of 34 squared as equal to 8 plus 6 over 20. So the approximate fifth root of 34 squared is 8.3, which is close to the exact fifth root, which is 8.2964.